icon. There we go.
There. Aha. Okay. So, hello everyone. Thank you for the chance. I mean, I'm always happy to talk to people about what I do because I like it so much. So, hopefully, I can do justice to the slides Elisa put together, and the organizers kindly changed my name. But okay, so this kind of talk is going to be a little bit different from the one we had before, because I'm going to talk about stuff we can answer and not stuff we can't answer. So take it as you will. So let's start with, I got this right? Well, let's start from what we do know. So one of the things we know, and this kind of ties into one of the points made earlier about astronomers being archaeologists, is that light travels at a finite speed in our universe, which means that a light beam traveling from one point to the other is going to have a set speed, and it's going to take a certain time to reach that observer. And this was something that was theorized initially by Romer in 1676, and people didn't believe him, of course, but it was very, people in the community of astronomy was very interested, like how hence Isaac Newton and so on, and a few decades later it was kind of experimentally found as well. But this is true for light, that it travels at a speed that is constant. And this has a big consequence for us in astronomy, which means that any object that has a distance from us, we actually don't see it as it is right now, but we see it as it was when the light left that object. So, for example, when we look at the sun, actually what we're seeing is the sun about 8 minutes ago and not the sun right now. So if the sun was to disappear at this very moment, we wouldn't know for another 8 minutes because the light hasn't come to us to tell us. And that's interesting because, of course, every galaxy we see that's very far away from us, every object that's very far away from us, we also see it as it was that many years ago, as much time as it took for light to travel. And that's why we call it light years. It's how many years it took light to travel. So something that's a million light years away means it's a million years in the past. So the other thing about light is, this was hinted at the quiz, was this redshift. So the fact that galaxies that are away from us, they are not only, the light is not only old, but is also redder, just because of how the universe expands. And we can actually use this information. We can use this information to kind of shift the light back to where it should be, because we can tell this in our labs, and we can find out how far that galaxy is. So that's one of the ways that we can actually map out the universe and kind of build these maps and these data sets. So we kind of have an idea of what this chronological map of the universe looks like, and of course we both talked about whatever concerns this period over here, which it's very hard to study because there are not many observations that can actually tell you a lot about this area. But we also have this kind of starting point that we call it in kind of observational astronomy maybe, this cosmic microwave radiation, this afterglow of the light finally being able to traverse in the universe and shining through. And well, later on, so this is the moment right here, which is the earliest moment that we can actually see, and we see this in the kind of the radio band of our instruments, and then this is where we are today. So the light from these galaxies have traveled all the way here, but in the meantime, all these kind of seeds that you see in this kind of map, they kind of tend to grow and form this structure that we know today, these stars, and then galaxies, and then galaxy clusters, and so on. And this light looks like this, and it's kind of like a treasure trove for cosmology, because there is a lot of information that we can extract from this kind of data. So this snapshot of the universe at the very early ages, it was first discovered accidentally by Penzias and Wilson using this kind of horn, and the story goes that they had this interference in the microwaves, and they thought, what is this? It could be pigeons causing this or whatnot. In the end, some people in, I think, Princeton got in touch and said, okay, this is actually cosmological signal. And what we can actually do with this kind of map is we can we can't really tell much from each individual speck in this map, but we can actually make sort of correlations between these specs and these actually encode a lot of information about what our universe is made of, what is the kind of the geometry of the universe, and how did it all began. And what we end up learning from doing this kind of analysis is actually that the universe, we don't really know what the universe is made of, unfortunately for us. It's quite embarrassing to show this slide in talks, but I'm sure you've all heard this before, that we only know about 5% of the universe, and the rest of 95 is kind of this dark matter and dark energy. And what this really means is that this 5% of the universe, we kind of know how it behaves, and we have our theories of physics basically describing this component. So we know what it should look like in our universe. And then when we go look at our data, we see that that doesn't match. In order to make them match, we need to assume that not only we have this 5% of ordinary matter, but we also have this 25 or so percent, 26.8, the latest measurement, of dark matter. What is dark matter? Well, we have to put it in the equations, and we have a few ideas of where this actually manifests in the universe. But essentially, it's just matter that doesn't have any interaction with anything. If you shine a light on it, it's not going to bounce back. If you put it in a box, nothing's going to happen. It just has gravity, and since it doesn't interact with light, you can't see it. We call it dark matter. And then we have this other component, which we call it dark energy, and is actually responsible for the expansion of the universe. And we see that actually the expansion is accelerated in the later stages of the universe. So imagine the Big Bang. You can think of bang explosions. Okay, you expect things to not speed up, but kind of either slow down or maybe come back together. But in fact, we see the universe speeding up as if someone is pumping it from inside, and that's what we call dark energy. And these are open questions in physics, and cosmology is one of the biggest open questions in the field. We have some ideas of what it could be. So for dark matter, we have written down exotic particles that we don't really know if they exist or not, such as these WIMPs and these axions and so on, that could actually be dark matter particles, could actually explain this component of the universe. There are a few other ideas, such as missing objects, some objects that we can't actually see because they are too dim in the sky, or maybe the universe is full of black holes that are too small to actually observe, but enough to matter. So we have ideas for dark matter, and we also have some ideas for dark energy, which could be some kind of constant in the universe created by quantum effects, but actually the math doesn't seem to work, so we don't know about that. Maybe some fields, some extra field in the universe, like we heard about fields before. Physicists like their fields, so we could one for dark energy. Or maybe our theory of gravity is incomplete, so this is not the first time it's happened. Of course, we had Newton's gravity, and it turned out that was incomplete. And we had Einstein's gravity, and maybe this is also incomplete. So this is kind of the big open questions of the next few years. And we saw already this kind of ultrasound of the universe, this baby picture, this cosmic microwave background, is able to answer this. But it would be nice to be able to have something that is independent of that observation in order to verify our measurements. And that is the reason why we go around building telescopes and observing the night sky, because we can actually use observations of galaxies to learn about the universe. So this is kind of a similar map as before, but now every dot in the map is a galaxy, and it's color coded according to distance. So the redder the galaxy, the further away it is from us, and vice versa over here. And we sort of, the idea is that we build these telescopes, and we go out in the night sky, and we try to map out the galaxies in the universe, and try to use the galaxies as kind of tracers of the field. So it's like if you imagine you have a sort of a landscape you can't see, but then you start putting little specks of sand on it, then you can actually see the sand, and you can figure out the underlying distribution. And so this is one way is to map the galaxies and map their locations, but actually it's also very useful to measure the galaxy's shapes. So this is an extra information that we can leverage. And this ties back to another thing that you saw in the quiz, which is gravitational lensing, right? So according to the theory of gravity from Einstein, the theory basically describes how the matter curves the space-time and how space-time tells matter how to move. and that's a consequence from that is what we call gravitational lensing, which means that if there is something that has mass in the universe in some point, around this mass the space-time is bent, which means any light traveling from behind this object to us will have like sort of a curved path, and its shape will be distorted. And this kind of phenomenon depends on, of course, the mass of the universe. So we can study dark matter, because of course dark matter doesn't have any light, but it does have gravity. So that's one of the best ways to study it. And we can also study dark energy because, well, the light has to travel through the universe, and because of this we can actually understand its expansion history. And that's kind of the pinnacle of galaxy surveys in the last few decades. And there's been a lot of different surveys from different telescopes around the world trying to measure these things, try to measure, to build these maps of galaxies. One of them is called the Kilo Degree Survey, which is now completed. And I'm a part of this survey as with Elisa, and we're trying to analyze the last data from this survey. It was, the headquarters, let's say, was here in Leiden, so we're very proud of this. And it used the telescope of ESO in Chile to map out 21 millions in the galaxy up to 9 billion years ago. So in terms of the universe history. And what we actually end up measuring from this kind of surveys, as I said, we have a shape of a galaxy, which, I mean, the galaxies look like this, so you can see how difficult it might be to measure a shape there. And you have a position in the sky, and then you have a distance of a galaxy from us. And sort of using these numbers, we can kind of try to understand a little bit more about the universe. So we can use this kind of distortions, these positions and so on, and we can literally map out the matter distribution in the universe. So this is kind of a, if you want an X-ray of the matter in the universe using this technique of lensing. Wherever there is a bright spot in this map, it means that between us and the universe there is a lot of matter along this direction, and then you have this kind of wobbly structure as well, like you might have seen in other parts of other different data sets. So it's really great because, as I said, we can use this kind of tool to study dark matter in the universe, and we can sort of do a little bit of archaeology of the universe as well by splitting our galaxy data into distance from us. So what I mean by that is if we are here today and then we try to make this map using galaxies in different distances, that means the further away we look, the further back in time we look. So we can do this kind of universe archaeology, kind of play this kind of game where we can really understand the history of the universe, and that really tells us a lot about how the universe expands, and really helps us understand more about this dark energy of the universe, and also test our theory of gravity, and see if our current theory of Einstein is correct. So far, all the tests have passed, but this is where we stand today. However, the future of this is quite bright. There are many surveys that have been completed. As I said before, I showed you one, but there are a number of other ones that have done the same thing with different parts of the sky or different data. So it's good to actually cross-check the results with different surveys. But in the near future, we'll have new telescopes that have been built or are actually already observing. So this is the image here is from the Rubin Observatory, which is a telescope in Chile. It's about it's housed in this dome, and it's about an 8-meter mirror. So it's really good about in detecting very faint stuff, which means if something is very faint, it means it's very far away. And it's going to start taking observations in 2025. It's now kind of being assembled and being built, and all the components are being shipped and assembled. And it's going to be able to observe galaxies up to 11 billion years ago. So if you think about it, the universe is about 14 billion years ago, so we're actually reaching the time where we might actually be able to observe almost all the galaxies in the universe. So then we have to find some different ways to do science. So this telescope is going to start observations around 2025, but the camera is already at the site, so that happened a few weeks ago. And here you see the camera over here, which was taken in July in SLAC, which is the Stanford lab in the US. And I went myself to see this camera in some kind of collaboration meeting, and it's truly incredible because the dimension of the lens is like a meter and a half, and it's actually the largest digital camera built in the world. And this thing has about, I think I say 3,200 megapixel camera, so it's about as good as a selfie camera. Very impressive technology, and this telescope is kind of pushing the limits of what we can do and making new frontiers. But it's not the only thing that is pushing the limits. Another telescope already operational is the Euclid Satellite Telescope. So this is a very important mission from ESA, which actually launched about a year ago in July 2023, and is now out in space, taking observations and collecting data, and it's also kind of a big step up in what we could do before. This telescope is going to push the boundaries even further in terms of the quality of the data, the amount of data, and so on. So the future for cosmology is bright, at least observational cosmology. I'm not sure about what Subodh was talking about. So okay, here is some of the images that this telescope has taken. So these are from some of the press release, and where you see a spiral galaxy over here, and some globular clusters. So these are clusters of stars around our galaxy, or a big cluster of galaxies over here. So all these little elliptical blobs are part of the same structure of galaxies. Or we have imaged also molecular clouds. So this is I believe is the Horsehead Nebula in the Orion region. So these images were kind of part of the commissioning process, and things seem to be working well, and we look forward to kind of getting our hands on the data and analyzing them and getting to the bottom of all this. So this is kind of a zoom in into this kind of cluster of galaxies where you can see kind of the power of this telescope and the quality of this data. So what I showed you the first time, the Rubin Observatory is from the Earth. The benefit of this telescope is that it's in space, so it doesn't have to deal with effects of the atmosphere of the Earth, so it can take actually really pristine images. Okay, so that's more or less about cosmology from an observational point of view. So a little bit more about what we do in Utrecht. And as Jeger already mentioned, we actually deal with tidal effects in galaxies. So these are not very dissimilar from tidal effects in Earth, which you might have seen if you went to the beach. So what's happening here on Earth, for example, is that the effect of gravity from the sun and the moon is actually making the oceans bulge, and then as the Earth moves inside this bulge, you have these tides coming in and going out. You have the high and the low tide, and similar physics can happen for galaxies, but in much larger scales. So, for example, if two galaxies are very close together and their gravity affect one another, you can have these tidal interactions where these galaxies are actually going to align with one another. So, if before they had a kind of a random orientation in the sky where their axes were pointing in a random direction, through the interaction with each other, through interaction with the gravity of the universe, they're going to actually be affected by this, and they're going to have some kind of signal present in the data that we can actually extract. And this is what we're busy with doing in Utrecht, trying to figure out, study this phenomenon, figure out ways to use it, and in the broader context of cosmology, and go from there. So, okay, my take-home message from the talk is the largest open questions in the universe are about dark matter and dark energy. Not to overshadow, of course, what Subodh was talking about inflation and the Big Bang and so on. Those are also really large, but as you heard, maybe we have less of a hope to answer them. And so, one of the ways to try to understand these components is to go out with our telescopes in the radio bands, in the optical bands, in all our different ways to see the night sky, and try to just make maps of the universe and put those models to the test by coming up with statistics that describe those data. In particular, one of the ways to do this is with measuring the shapes of galaxies in our universe, measuring the distances and their positions, and try to figure out how gravity actually distorts those shapes. And well, if we can figure this out, then we can figure out how gravity works, what's our universe made of, and what's its history. And it's actually quite an exciting time because a lot of these new telescopes are actually coming to light. They're taking data, and the next decade or even more are very hopeful for us astronomers. So thank you for your attention, and I'm happy to take questions.
Okay, thank you very much, Christos. Especially since I think it was the second time you saw these slides. So, does anybody have any questions? Yes.
You talked about tidal interactions of galaxies. Is that something that we can already see happening with Andromeda in our own galaxy?
So they're not close enough to actually see these interactions. So let me try to go back. Right, so these galaxies are particularly close to each other and might already have passed through each other, so that's why you get these kind of streams. So that's not something we can see right now. But if you wait long enough, and that might be quite long, you will be able to see this. However, I mean, the gravity in the universe is everywhere. So we have this thing we call the gravitational field of the whole universe, and this is dictated by the matter in the universe. The universe is not empty, of course, so it has some kind of matter distributions and has some kind of gravitational field, and that field is going to affect the galaxies. So that actually we can see it, but we cannot see in one galaxy because looking at one galaxy you can't really say much. But we can see it statistically if you kind of statistically ask the question, where do galaxies point to? Then you find out that the galaxies are pointing towards other galaxies. And then you think, okay, well, where do galaxies live? Galaxies live where there is a lot of matter. So then you actually say that, okay, galaxies are pointing where matter exists, and that's kind of in line with what we expect from theory. So that's kind of how we do this.
Okay, let me ask a question. So you say that with Rubin and Euclid we will be able to measure almost all the galaxies that have ever existed. So after this is done, do you have any feeling for what will be the next interesting questions, or won't there be any interesting questions left?
It's over then.
I hope not, because I'm looking for jobs. So, I mean, it is a very good question. So, mapping out all the galaxies, that's great, but there's still lots we don't know from this kind of data. For example, we don't know the chemical composition of the galaxies. So for that, you would have to do extra observations that are a little bit more difficult to do. And we also don't know the distance to those galaxies with arbitrary precision. So there's always a kind of a trade-off. If you want to get a distance precisely, then you need to spend a lot of time observing, and that means we don't get a lot of galaxies. So we have kind of a trade-off there. But at the same time, galaxy service is one part of the whole puzzle, but of course there's the CMB, and we've observed the CMB many times, the cosmic microwave background, as I said before. But there's still a lot to learn from that, so maybe the next generation of satellites are going to observe it with higher fidelity. And then the most obvious thing is the new frontier in astronomy and cosmology, which is gravitational waves. First detected in 2015, and now there's many missions that are actually aiming to observe gravity waves from galaxies merging, from the initial kind of violent inflation of the universe that you've heard before. This phenomenon is going to cause space-time to vibrate, and we can actually hope to see these vibrations with future missions and many other things. So I think that's one of the biggest frontiers in the next decade. Of course, there is also the question of how do we interpret that data, which comes with challenges, but I think it's really exciting. And there's lots to learn, so hopefully have a job in the next year.
Following up in the question, so the universe has 14 billions, we are going to observe until 11 billions, so it means in the first 3 billions we already have galaxies?
Right, so if I go all the way back, then you will kind of see what the history of the universe, what we think it looks like, right? So this is time 0, if you think of it linearly. This is 400,000, right? And then you have this called of dark ages, kind of ominous term, but it just means that there is matter in the universe, but it hasn't come together enough to actually produce things that shine a lot. But eventually it will, and then you start forming stars, and you have this moment in time where you start having visible stars, and that's about 400 million years ago, so still not quite a billion. And then we start forming galaxies. So, and here we're at 14 or so. So we still have, if we are at 11 now, we still have another couple to go. So, and this is the biggest challenge, because the galaxies over here are really dim, which means it's really hard to observe. But they're also really important, because a lot of the physical processes that govern the universe happen here that we don't know for sure. And actually there are a few surveys that are trying to do this, not with telescopes in the optical, but with telescopes in the radio. Because it's easier to go back in time with radio, because it's easier to find galaxies here in radio bands. Because of course galaxies get redder, so at some point you get so radio in the radio. So yeah, there's still galaxies around.
I understood that there are black holes too heavy in the universe to be explained by what we know by now. Yeah. Is that a subject to be researched in the near future?
Right, yeah, so this actually ties into this image. With the new telescopes like the JWST, which is specifically designed to find galaxies around these early times. The downside is you can't find too many, because you have to look at them for too long. We see that there are some galaxies that seem to have too big of a black hole. So from the point of inception until point of observation, there's only so much time. So there's always the question, how does a black hole grow so massive as we see it in so little time? So this is an open question. There are many facets to this. Maybe we need to revise our models of galaxy evolution. Maybe there's already some seed of black hole from before this time that is there. So you don't have to grow from 0, you have to grow from already a seed, and that makes it possible. But there's always the unknown possibility that some observation effect is not well understood, or so on. So I'm not an expert on this field, I just know a little bit about it. But it's certainly an open question, and by getting more data from galaxies over here, we hope to try to understand it. Yeah.
Okay, final question all the way in the back.
I'm not sure I know how to answer or ask this question, but you said that as the galaxies tend to point more in the same direction as time goes by, much like the solar system exists.
Yeah.
How far can that process go? Could the entire universe be full of galaxies all in the same way?
Right.
And how far are we along that process?
So, right, so galaxies tend to align, but this alignment is with respect to the distribution of matter, right? So if you had all the matter in the universe all in one spot, and you just put galaxies around, then all of them would point to that spot. But that's not really what's happening. The universe seems to be, there's no preferred direction from what we can tell. So then where do galaxies point to? They point to their local density maxima, let's say, right? So if you have a lot of matter here, lots of galaxies around, they're actually pointing towards there. And then if you look at larger scales, then again they point towards where the largest. And then when you go to the super large scales, where the matter is kind of homogeneous, then you stop really seeing alignments anymore, because they don't know where to point. They're pointing to the local sort of environment, local to some extent. Like these are like astronomical scales, literally. But yeah, so eventually things tend to look out homogeneous as we look in very, very large scales. And if they don't, then we need to think about it.
Okay, thank you very much, Christos. Let's thank him again.